Hey, welcome everyone into the NGK Tech Garage. Thanks for joining me today. Today, just like the title suggests, we are going to cover knock sensors. We're getting into knock sensors. We're going to do a little bit of theory on knock sensors and kind of the way the engine is going to run and why we have knock sensors. And then we are going to cover the diag on this 06 Sienna here, and then we're going to get into the actual repair of the vehicle today. So I apologize in advance. I do have a little bit of a cough today. Taking cough drops, just, you know, tis the season. So before we get into it, I just wanted to cover a couple really quick things. Vision training event was last weekend. It was a fantastic event. If you guys didn't get to it this year, make sure to mark your calendars for the event next year. It is well worth the travel to Kansas City to attend that event. It's fantastic training. Meet up with a bunch of really cool people. I met up with a bunch of you guys in the chat. It was overall a great event, learned a lot, met a lot of great people. With that being said, I am going to the TST big event coming up here at the end of the month. If you haven't already looked into that, go ahead and check out the TST website for that and get yourself scheduled to go to the big event. It's a Saturday event in New York, so try to make it out to that and just keep training, right? If you got the time, if you have the funds available, make it out for those training events. Also, it's official, guys. We have new shirts. Finally, we have new shirts. They have the logo on the chest here, and then on the back, diagnose before you triagnose. All right, so we are going to be giving shirts away, but there's just going to be a couple little changes from the way we used to do it. The shirts are going to be given away. The question is going to be asked at the end of the broadcast instead of the beginning. That way you guys don't have to be worrying about typing me out an email during the training or anything like that. We're going to ask it at the end, and then we are only going to pick 5 winners. The first 5 people to send me an email with the correct answer will be the winners. Now, if you've won a shirt already, we're talking months down the road, but if you've won a shirt already, we're going to try to let the other people win, okay? You can still submit an answer, but if you've already won and you were ahead of somebody else who hasn't won, we're going to go ahead and bump those people up so that everybody has a shot at winning a shirt. But still submit your answer. We will send you another one if there aren't other winners, okay? So that'll happen at the end of the broadcast. If I forget, please remind me so I don't forget. No pocket on this one, unfortunately, guys. I know a lot of you guys have been asking for a pocketed t-shirt. No pocket on this one either, but maybe on the next one. Okay, I think that is just about it. So let's get right into it. We're talking knock sensors today. This has a P0333 code in there for a knock sensor circuit high code. But before we get into the actual vehicle, let's talk about what exactly a knock sensor is and what it does on our vehicle. So right here is a knock sensor. This is actually the one that would go on this vehicle. And a knock sensor is basically it's called a microphone or well, it's a sensor, but think of it as a microphone for the engine. It is listening for a certain frequency, a certain amplitude signal to be received and send it off to the PCM to retard the ignition timing. And that is the goal of the knock sensor. It's listening for knock or pinging or detonation. They're all kind of interchangeable words there. But it's listening for those events to happen. When those events happen inside of the cylinder, it will cause an output of the sensor. The sensor will create an AC voltage, send that signal off to the PCM. The PCM will recognize that signal, and it'll retard the ignition timing to stop knock from happening or stop detonation from happening. So before we talk exactly what detonation is, let's just talk a little bit about the combustion event in the cylinder. So we close the valves after our intake stroke. We get air and fuel into the cylinder, and we bring the piston up on the compression stroke, and then we ignite the spark plug, right? So what we're really looking at when we ignite that spark plug is the combustion event. Now, I've talked about it as an explosion in the past. It's not really an explosion. It is a slow, controlled burn. So this is the event that's actually happening inside of the cylinder. Now we're talking in milliseconds here. This is happening very quickly at 6,000 RPM or whatever it might be, but it is a slow, controlled burn. It's not a spontaneous explosion, okay? It happens slowly, it expands outwards, and it's even. It's a controlled burn And that explosion, that burn is creating pressure inside the cylinder and forcing the piston back down on the power stroke or the expansion stroke. And that's where we're getting the power for our engine, okay? But if we all of a sudden ignite that mixture very quickly, if there's an issue inside of the cylinder, so if we're, like let's say we're at this part of the event, and all of a sudden some of this end gas here spontaneously combusts because of high heat or high pressure inside of the cylinder, now we have these two pressure pulses that are going to bounce off of each other. They're going to hit, and that is going to send ringing or knock through the block, and that's what our knock sensor is picking up on, okay? So our combustion event is going to hit the detonation event, and it's going to bounce off, and we're going to get that ringing through the block. That is why we have a knock sensor, because we have to listen for that. A lot of our newer engines like to hover right in that line of detonation, right in that line of knock. So we're gonna advance the spark as far forward as we can, because that's how we get more power. Our goal here with this combustion event is to receive or obtain our peak pressure inside of the cylinder at 14 degrees after top dead center. So the piston's starting to make its way back down. We want to hit peak cylinder pressure at 14 degrees post top dead center. Piston's heading back down, we hit that peak pressure, and we're forcing the piston downwards. So when an engine's spinning slowly at idle, we maybe have a few degrees of ignition advance. We have to fire that spark plug early to start this event to obtain that 14 degrees. But we start to spin the engine up faster. We're up 3,000, 4,000, 5,000 RPM. We have to be able to get that spark to happen sooner, so that way our controlled event can still hit that peak pressure at 14 degrees top dead center. But if we fire it too soon, we allow too much heat and pressure to build inside of the cylinder with that spark firing early, and we end up with those pulses hitting each other or hitting the walls or hitting the piston and causing our knocking issue. So we run into detonation, our engine pulses are bouncing off of each other inside of the chamber, and the engine starts to knock. The knock sensor starts to pick that up. It's a microphone, right? It's listening for that to happen. It picks it up, sends a signal off to the PCM, and then the PCM will retard the ignition timing. It'll make the ignition event start later. We're starting it too early. We're creating knock, we're creating detonation. We have to make it happen later. Now, what exactly can cause that detonation to happen? Fuel octane and temperature are big ones. Mechanical timing, obviously ignition timing, right? That's what the PCM is going to adjust to change that from happening. Our compression ratio, the actual design of the chamber, and of course our air-fuel ratio itself. So before we get into octane, let's talk a little bit about temperature and AFR. If our air-fuel ratio is running lean, we increase cylinder temperatures. If our engine is overheating, we increase cylinder temperatures. When we have a hot cylinder, it's more likely that those end gases, the part that's not a part of the combustion event, it's more likely that they can spontaneously combust, and we can end up with knock. So a hot cylinder or a cylinder that's very high on pressure because of a high compression ratio or an intricate design of the chamber can cause that to knock as well. That's why higher compression engines you'll see running higher octane fuel. So what is fuel octane? The octane of the fuel that we run in our engine, this is an 87 octane fuel engine, standard regular pump gas. If you run an engine that's a higher compression ratio or maybe a more, it's called a performance car, whatever it might be, you're going to want to run premium in there if that's what's required, because when you're running a higher octane, 91 or 93 or even race gas or ethanol or anything like that, the higher the octane number, the more resistant that fuel is to knock, the more resistant it is to detonation, the more resistant it is to temperature and pressure inside of our chamber. So if you take a car, let's pretend this was a sports car, and it was running 93 octane fuel, we can run more ignition advance on that engine because that's what it was intended for. If we put 87 octane in this vehicle that requires 91 or 93, we might not end up with a check engine light. We might not even notice any difference, but if we were to data log the ignition advance, if we were to measure horsepower output of the engine, if we were to measure our track times, we would most likely end up with a slower vehicle, worse performing, and more retarded ignition timing because the engine will start to knock because of that fuel change inside of there. So 87 octane in a 93 octane vehicle can cause knock, and that's why we have knock sensors. Without knock sensors, that engine would be knocking consistently and could potentially cause some severe damage. All right, so that's a little bit of theory. Let's make sure I don't have any questions. Everyone's giving Mike a hard time. Yeah, that's usually what happens here. All right. Now, knock and pre-ignition are commonly talked about in the same sentence, but they're very different events that happen inside of the cylinder. Pre-ignition is an event that happens just like it sounds before the ignition event. So we haven't started the combustion event. We haven't expanded inside of the cylinder yet. We haven't started that flame front. Pre-ignition happens when there's something hot in the cylinder, whether that's a chunk of carbon or the spark plug is the wrong temperature, maybe a valve is overheated. Something has caused the combustion event to start before the ignition event started. Now, engines are not designed to handle pre-ignition by any means. You usually end up melting something down incredibly quickly when you have a pre-ignition concern. This is where you end up with the hole right in the center of the top of the piston. That's caused by pre-ignition because the engine is igniting before the ignition event. We can't take a knock sensor and retard ignition timing to change anything. It doesn't do anything for us because we haven't even fired the spark plug yet and we're ending up with pre-ignition. Detonation happens after the ignition event, pre-ignition, before the ignition event. We can control detonation with knock sensors. We cannot control pre-ignition. Okay, so they're two very different items inside of our cylinder. Also, pre-ignition is most likely to happen at the lower pressure point inside of the cylinder. As we bring a cylinder up on pressure, it becomes harder to ignite that fuel, right? We take more spark energy, the higher compression that we have. So to pre-ignite a mixture before we fire off the ignition event, it's going to most likely happen somewhere near bottom dead center inside of the cylinder. Because we have the least amount of pressure, we have our air in there, we have our fuel in there, but we haven't really started to squeeze it yet. So now, as the piston's coming up on the compression stroke, it's being driven by all the other cylinders. Now we have a fiery combustion event happening in there way before it was supposed to, and we're trying to compress that event. We have tons of pressure and heat buildup on top of that piston. That's why pre-ignition damages so quickly inside of our engines. We cannot control that pre-ignition event like we can detonation with a knock sensor. All right, Wesley has a question on, can scan tools now determine which cylinder is knocking? I don't know if they can pick out a single cylinder. Maybe if they have multiple, maybe if they have a single knock sensor for each cylinder, potentially. Actually, we got the snap-on scan tool hooked up right now. We hooked up the launch. We hooked up the Autel. On this vehicle, I have no knock sensor PIDs whatsoever. I have one ignition advance PID that we'll look at here in a little bit, but I don't have any PIDs about knock sensors, whether the engine's knocking or not, knock sensor voltage, knock sensor signal, none of that. No control with any of the aftermarket scan tools that we have for this vehicle. So I don't know. Now, this engine, we can see knock on each bank because this one will run two sensors. So we'll have a knock sensor for bank 1 and a knock sensor for bank 2, but this one does not have individual control. Now I wonder, maybe if we were to add more knock sensors, if we had one by each cylinder, there's probably an engine out there that is able to see knock on each cylinder. It's possible, right? All we're looking for is something in the cylinder to happen that's not supposed to be there, and that causes a ringing event inside of the cylinder. So let's talk a little bit about the signal out of the knock sensor, because a knock sensor it's tuned for the engine, okay? So just like a tuning fork for music, right? It's going to do a certain pitch. If you hit that tuning fork, it'll give you a certain pitch, a certain frequency of output from that tuning fork. A knock sensor is the same way. We tune the knock sensor for the frequency of detonation on that engine. So knock sensors aren't interchangeable. They're super specific and tuned for each engine. They're meant to knock or make noise at a proper frequency and a proper amplitude within a certain amount of range that engine is recorded to have been detonating or knocking. So this one, I believe, according to service information, was between 6 and 15,000 hertz, this sensor is tuned to create a signal. But you'll see, if we look here, you'll see the signal change dramatically as we get up into the, let's call it the sweet spot of what the sensor's tuned for. So what I've done in this lab scope image here is I've taken a knock sensor for this vehicle and I've put it on our knock sensor tester, okay? So we have a tester in-house here because we manufacture knock sensors. So here is individual testing events running through roughly 1 hertz all the way up to 25K hertz, okay? So 1 to 25,000 hertz. Here is one event, and if we look, here's our sweet spot, okay? This is the sweet spot that the sensor is tuned for, okay? So Toyota, this PCM right here, is calibrated to look for a certain level of amplitude and a certain frequency to happen to determine knock. The sensor will most likely always create some sort of voltage. It's a voltage generating sensor. It's going to create voltage all the time, but the computer is not going to be fooled into normal noise. Every engine makes noise. There's resonant frequencies inside of this engine that will always be making noise, right? But it's that specific tuned noise that that sensor is looking for on here that designates knock. That's what the computer is looking for. It's that specific frequency. And right here, we can look, and we'll just look really close to the peak. So we're super zoomed in right now. This is 1 total millisecond on the screen. So let me throw a ruler up here, and let's just measure this. So we're looking at 13,000 hertz right there. Okay, 13.28 thousand hertz. So super high frequency. I wanted to, my plan here was to find something that I could replicate the frequency and feed it to the computer to show you guys the ignition system retarding the ignition timing to simulate knock live on this vehicle. But unfortunately, I can't wheel our whole tester in here. I can't do that. And I couldn't find anything that I can hit 12 to 12-ish thousand hertz with. But to show you guys an example with this thing, I do have some leads hooked up here. And I'll show you just how fast that actually is and why it doesn't do what we would hope it would. So I have hooked up to the lab scope this knock sensor right here, and I guess I'll hook it up to the meter as well. If we can bring up this camera in the lower corner, I think what we'll do here is we'll show it with both. When you're testing knock sensors, you don't have to really have a lab scope. It's nicer to look at it, but the voltmeter will look at voltage, obviously, to look at the AC signal, and it can measure the frequency, the hertz as well. So I'm going to do it with both just so you guys have the option to see both. So I just set the meter on frequency, and if you guys are full screen, you should be able to see that. And I'm just going to piggyback in on the lab scope here. And I'm going to go ahead and X out that one because that was about, what, 12 to 13,000 hertz. And we'll get this booted up. All right, we can bring the lab scope up on the screen. And I'm going to go ahead and we'll increase our time. And we'll zoom in from here. I'll just put a second per division up on the screen. So we're looking at 10 seconds in total. We'll look at some AC signal. I could measure in frequency as well, but we looked at AC on the other one. So I'll measure that as well. And we'll see what 10 volts looks like. So frequency, again, is the amount of times that something happens per second. So if I tap this on the table right now, we have 4 taps there, right? 4 times I hit it on the table. That's the frequency that we're happening right now. If I tap it faster, we get more. Amplitude is how hard it's being hit. The signal output will depend on the strength of the vibration. So if I hit this really hard on the table, we create more voltage, right? So the PCM inside of this Toyota right here is not only looking for the proper frequency to happen. Man, I just struggle with that word. I don't know what it is. The proper frequency to happen, but it's also looking for the proper amplitude. We have to overcome a certain limit, because actually on this Toyota, we'll get into the circuit in just a minute, but we have a reference voltage circuit on here to check for circuit integrity. That's why we can set circuit codes. So we have to overcome the reference voltage in order for this sensor to even be seen, and then it has to be in the proper window to designate knocking. So what I did for a little experiment here was, we got a little impact right here, right? Spins pretty fast. I don't know what the RPM is on this thing, and somebody will ask, somebody probably has an answer. It doesn't really matter at this point. But what I can do is I can put a socket on here and have it kind of wobbly on the end. If I spin this around, this is a locking extension here, so it's not going to go flying and hit me in the face. But what this will do is this will spin around at whatever RPM it is, and that will replicate a frequency on the sensor. So if I spin this around and hit the sensor with it, you'll see the output. So let's bring them both up on the screen. And we should see it on the meter as well. Okay, here we go. So we're creating a high level of frequency and amplitude. So we're reading almost 1,000 hertz at some points there. But that's nowhere even close to the 12,000 hertz that signal's reading. And if we look at it on the lab scope, this is why I'm not able to induce the signal onto the PCM here to make this thing think that it's knocking, because I'm not even close to the frequency that the computer's looking for. So if I go frequency again, measure between my rulers, I'm reading, well, in between this spot right here, I'm reading 38 hertz, okay? Not even close to as fast as we need to be to get this computer to think that we have a knocking condition. And that's just the PCM's way of filtering, right? It's filtering out the noise. It's looking for a hyper-specific spot that is knock. That's what it's looking for. Knock makes a specific noise, and it's looking for that specific spot, that hyper-specific moment when we have knocking in the engine. We retard the ignition timing until the knocking goes away, and then slowly but surely the PCM will start advancing it back, looking for that knocking condition. Again, it's going to vary on load, it's going to vary on temperature, it's going to vary on the fuel that's in your engine. Theoretically speaking, a more volatile fuel will have a higher chance of knock, right? So when we run winter blend fuel versus summer blend fuel, the probability is that in winter I would have less ignition advance because I have a higher volatile fuel, right? But it is still 87 octane. So that might be a good experiment for you guys to try and run at home, playing around with watching ignition advance compared to different fuels. You could run E85 versus standard fuel, standard 87. They're all going to have different characteristics. If you change compression, if you add a turbocharger, if you change VVT, if you open EGR, if you change the purge solenoid, anything that's going to affect temperature, anything that's going to affect pressure, anything that's going to affect what's going into the cylinder is going to affect knock. And that's why we're constantly watching the knock sensor to make sure that we're not causing engine damage. Now, like I said before, most engines can handle some knock. They kind of are right on that level, right on that borderline. But we want to be able to make that, stop that from happening as quickly as possible. Okay? Let's just check, see if I had any other notes here. Again, combustion is not an explosion, it's a steady burn. Octane is resistance to knock. Okay, any questions on knock sensor theory on what I covered before we get into the actual diag on this vehicle, and then I am going to actually repair it. So any questions quick? And Steve, you're exactly right. If I could get a hammer to hit the block 65,000 or 6,500 times per second, sure, I could induce knock on that engine. I could make the PCM think that we're knocking. If I could hit it with 10,000 beats per second onto that engine, I could induce knock, and I could probably get the ignition system to retard the timing. But I don't I didn't have the ability to find anything that I could replicate that signal with. Also, make sure, a couple things with knock sensors, make sure that you're not having a knock induced by something that's not cylinder related. Engine mounts, loose sensors, something in the serpentine belt drive, maybe something loose in the timing belt or timing chain drive. Anything that can cause a harmonic vibration in the engine block, which is what the knock sensors are directly connected to, anything that can vibrate at that frequency and cause that knock sensor to pick that up can be induced as knock. It doesn't have to be happening inside of the cylinder. So the knock sensor is completely blind to anything besides harmonic vibration, frequency. It's looking at that. It doesn't know if it's happening in the cylinder. It doesn't know if it's happening because it's a sweet spot with a loose engine mount or alternator bearing that's going bad that's hitting 12,000 frequency, 12,000 hertz. I mean, there's just anything can cause it. It can be incredibly hard to diagnose a knocking issue that's not coding or an implausible type signal code. Now this one is a circuit code, and it's really not going to be all that difficult to diagnose today, but we will get directly into the repair. A cat stuck in a fan shroud, that would probably induce some vibration, but probably not at 12,000 times per second. All right, so let's just take a real quick look at the code. I got to flip the key on. So again, we're working on an 06 Sienna, 3.3 liter V6 in here, and I already got it pulled up on the scan tool, so we'll take a look. We should see bank 2 sensor high, P0333 code. All right, P0333, knock sensor, bank 2 circuit high. Okay. No drivability concerns on here, just a check engine light on. When I open the hood on this thing, guys, as you've been doing this for a while, you tend to learn certain smells when you open the hood, right? You open the hood, you can smell burning oil. You open the hood, you can smell burning coolant. You open the hood, and you can smell mice, right, or rodents. You can smell that. They have that distinct smell of urine and a nest. You can kind of smell that when it's bad enough under the hood. It's just something disgusting that you just learn to pick up on, and immediately upon opening the hood with this engine hot, I could smell it. It smells like a mouse nest under the hood. Now, if we take a look under here, I don't see anything. But for whatever reason it is, Toyotas make good tasting wires. Whatever they cover the harnesses in, if it's soy-based or whatever it might be, they taste good to rodents. And we end up seeing rodent damage. And I would be willing to bet under our lower intake, and I can kind of see a little bit down there. You guys probably can't see it at that angle or any of the angles I have, but I can see a little bit of feathers and stuff hiding underneath there, under our lower intake. And under our lower intake on here is where our knock sensors are sitting. So I'm already thinking we have a circuit high code. We probably have a wiring issue for these knock sensors. Okay? It's just those things that you pick up on when you've been doing this for a while that you'll learn to look for those kinds of things. And this is kind of a no-brainer once we get that far, but you'll see. Okay, it is soy. I tested the wires myself. Yep. Oh, tasted, yeah. Lawsuits pending to prove it. That's interesting. So they like the wires on these. We've run into it before. But let's get into the circuit. So according to, well, let's start here because Hans gave me a hard time once because I didn't look up TSBs. So we'll pull a P0333. We'll just throw in an identifix here. And I don't have any related TSB specific to this code, but through my searching, I did find a related TSB specifically for knock. Toyota does have a ECM reflash for a knocking noise. I'm not going to go through the TSB itself, but it is a simple reflash to be done for relearning of some logic on here. But it's got nothing to do with the code that we have set. It is a knocking or pinging symptom, not a circuit code problem. So we'll get back to the P0333. And, well, knock sensor harness is common, knock sensors are common, so we just sell the job to the customer at this point, right? Diag is done. We smelled a rat's nest, mouse nest under there. We found it on Identifix. We're good to go, right? Well, what do we say here? Diagnose before you triagnose. It would really, really suck to pull the intake on here, get that job all done, only to find out that the PCM isn't sending the signal properly, or there's a wiring problem between the knock sensor and the PCM. We want to diagnose. So let's take a look at the actual DTC information from Toyota. P0333, output voltage of the knock sensor 1 or 2, 33 is for bank 2 obviously, is 4.5 volts or more. Okay, open in the knock sensor circuit. It could be a knock sensor, could be a bad PCM or ECM. So we just go down the list, right? Pull the intake, replace the harness, replace the knock sensor. If that doesn't fix it, replace the PCM and call it a day, right? No, we're going to diagnose this. We're going to do it right. Duration, so we start up the engine. It's a continuous monitor. We have to see 4.5 volts for more than 1 second on that circuit inside of the PCM. Enabling conditions, we got to be at normal running battery voltage, has to be 5 seconds after startup, and we have to have the ignition switch on. So this is a pretty common, pretty easy to replicate thing. So like I said, unfortunately I don't have any PIDs on the scan tool that will tell me knock sensor voltage, but we can go into data and I'll just prove it out to you guys. We do have ignition advance. And I did my homework. I ran through 3 different scan tools looking for this. I do not have access to Toyota, the Toyota scan tool. I don't know if that would have offered it either in terms of knock sensor data, but I went through each of these before this class. We'll just go in here and I'll show you guys that we have an ignition advance PID, which can be useful, but we do not have a knock sensor PID. So we'll just grab a custom graph. I'll deselect all. We'll grab ignition advance degrees. So again, we're making the ignition event start sooner before top dead center. And let's grab engine speed and let's graph those. So key on, engine off. We're currently sitting obviously at 0 RPM, 5 degrees advance. So let's just see if this engine will advance ignition timing with a knock sensor code. It's possible that the logic inside of the PCM says, no way, I'm not going to allow this engine to detonate. I'm not going to advance ignition timing because I see there's an issue with it. Or it's possible this PCM could say, okay, I have a bank 1 sensor that's not coding. I'm going to trust that one. I'm going to ignore bank 2, and we're going to go off of bank 1, and maybe we'll give it some ignition advance, but we won't give it the full amount. I don't know the strategy inside of the PCM. That stuff isn't shared with us. We have to kind of do comparative research, a little bit of learning as we go. So I'm going to start this thing up. We'll look at it at idle, and then we'll look at it under let's do 3,000 RPM, and then we'll compare that to the end to see what our ignition advance levels were. All right, here we go. Okay, bring it up to 3,000. All right. Okay, so I can't see the scan tool from in the car, so let's see what we had. Oh, I killed it. Rookie mistake. I turned the key off, guys. I might have to do that again. I know we saw some ignition advance. Can anybody tell me what we peaked at? Otherwise, I can do it again. Oh, let's just go back in the video. Looks like we peaked at about 25 degrees of advance there. Okay. Oh, we got even higher there. 39 degrees. Okay, I'll call that the peak. So we peaked at 39 degrees ignition advance. So this thing was advancing almost 40 degrees before top dead center with a knock sensor code currently stored in there. Interesting. We'll see when we're finished here if that's still the case. All right, let's take a look at the... So we know that we're seeing 4.5 volts at the PCM when when this thing is coding. So what does that mean? Let's take a look at a diagram. All right, now unfortunately it shares or uses two different knock sensors, or two different diagrams for the knock sensors. We'll just grab bank 2 because that's when we're testing, but we'll do some comparative testing between both. So this is going back to the PCM with both wires. We have a KNK2 and an EKN2, both feeding to the knock sensor. So the way this circuit works, on old cars, we might only have one wire going to the knock sensor because they might not have been monitoring the circuit for integrity. On this car, we're monitoring this circuit to make sure that the loop is okay, to make sure the sensor's okay, to make sure the wiring is okay. We're monitoring it at all times. So what's actually happening, the PCM is sending out voltage. Actually, let's go like this. Let's do this. We can draw, we can make a pretty picture here. So the PCM is going to send voltage down to our knock sensor. Now our knock sensor has this picture inside, okay? This is two different elements inside of the sensor. One, we have a resistor right here, right? We see these inside of relays, we see these inside of temp sensors. This is a resistor. Under normal non-knock situations, this resistor is acting as the load in our circuit. And when we put a load in the circuit, we drop voltage across the load. So the PCM is sending out 5 volts, and we should be dropping some of that voltage across this load. So the PCM should read a specific voltage in a known good circuit. Now this is going to happen key on, and this can also happen engine running. So if we take and measure voltage on this wire and this wire, we could also measure it here, either way. We want to look for a voltage drop. So I believe this is a 5-volt circuit, and if I remember right, we should drop about 2.5 volts. We should be reading roughly 2.5 volts on this circuit in a known good circuit. Okay, if we have a condition where a knock sensor were to be open, we would read open circuit voltage and we would read 5 volts, right, or whatever the PCM we're sending out. If that were the case, we'd set a P0333 high circuit code, which is exactly what we're setting. So that's why my gut's telling me that we're seeing open circuit voltage. We either have an open knock sensor or an open wire somewhere in here. We also have a connector right here, and that's where I'm going to be testing at today. Now, this sensor right here, this is the actual knock sensor. This is the piece that vibrates and creates our AC voltage, okay? When this happens, our AC voltage has to have high enough amplitude to overcome the reference voltage here, okay? We have to have higher amplitude than the reference voltage, otherwise it gets covered by the DC line. Our AC voltage amplitude needs to peak over that at the proper frequency to overcome the DC line, okay? So let's grab a scope. Let's grab the scope and we'll grab the multimeter. Throw this back on DC volts. We'll go, sure, 10 volts seems good. We'll bump this up to 5 seconds. I'm going to scope both channel or both sensor signals, and we'll throw it on the voltmeter as well, and we'll take a look at what we've got. Now, the knock sensor connector on here is sitting right underneath the air intake snorkel, kind of nice and easy to get to. Again, I did kind of prep this engine to cut down on time on here, but we're testing right back here. I'm going to pull this air box out of the way, so that way it should be easier for you guys to see. All right, so right here, maybe, let me get the camera so you guys can see it. That's our connector, okay? So I believe it was the red wire, and the signal for the other sensor is the black wire. So I'm going to go ahead and probe both of those, and then I'll throw the multimeter in there as well. Just because we don't need a lab scope to do this, it's nice to talk about using a lab scope because we can watch it over time. Because because then I'll actually start this thing up and show you guys what we're seeing. All right. So hook into battery negative. I'll hook into the red wire with channel. We'll go with channel 2 on the black wire, channel 1 on the red wire. So channel 1, or the blue channel on the scope, is the one we're kind of going to be expecting to see our problem on. And then, okay, so I do have the key on right now. We'll turn on channel 2. Okay, and then I'll throw the multimeter in here as well. Zoom you guys back out a little. Oops. And we'll go on the problem child one on blue. Hook that into ground. Let's grab AC. We'll go AC voltage this time. Okay. All right, so right off the bat, we have no AC voltage generation, right? Because we're not making any noise right now. If you want to jump over to the, yeah, there you go. We're not making any noise on the circuit right now, so we have no AC voltage generation. But if we look at the scope, we do have some voltage values on DC. So if I switch this over to DC, 4.137 volts. I think you guys should be able to see that, right? It's going to end up slipping and falling, and I'm going to lose my connection, of course. Okay. Maybe. Is that better? Okay. So 4.137 volts. We can look at that on the scope as well. And you can see we have two very different numbers here between our two channels. 4 volts-ish, 4.2 volts-ish, and 2.2 volts. So again, the red channel here is on our good side, the blue channel is on our bad side. So it's exactly what we expected to see, right? Our voltage is not correct. We have, they both should be at this level, right? Because we're going through the resistor. Now, let's go ahead and I'm going to fire this thing up. We'll take a look and see what this looks like with it fired up. I'm going to go back to AC voltage and see what we can see. So of course we're running without the mass airflow sensor right now. It's maybe not the happiest, but we got no AC voltage generated. And the red line got a little messier, right? Let's go ahead, I'm going to rev it up, and we'll see what we can see. I'm going to wait for the scope to refresh. And I'm going to bring it up to 3,000 RPM again. All right. So we can see that we've created voltage here, right? As we revved up, we created AC voltage. Now, it's not high enough amplitude, it's not a high frequency, but we have created voltage on our known good side. If we can just take a look at what we've got here, we're reading 160, 107, we're reading 15 hertz there, so we're reading low values on the frequency scale because we're not at that sweet spot of knocking, okay? So we have most likely open circuit voltage here, not doing anything. This side is causing, or the blue channel for bank 1 is good. And I don't think we saw any voltage come up on the voltmeter. So there's one other good test that we could probably do quickly. 2 tests, actually. We want to first of all verify the PCM side is good, and then we want to verify, maybe we can, let's do an ohm test, I guess. We can ohm test, this sensor has a resistor in there, so we can do an ohm test on the harness side. So I'm going to get these out of the way. Now I'll probably make a crazy mess with all the leads. But I'm just going to use we'll just use the voltmeter for this part. And I believe the PCM side should be just fine, right? Because we're reading that open circuit voltage. We're reading that 4 whatever volts from the PCM, but I guess it's just, we'll just verify really quickly that that's the case on the red wire and that it's equal to the other side. So if we can go to the, there we go. Actually, let's bring that up full screen. There you go. All right. So, of course, because I have the key off, we're not going to have any voltage. So now I'm going to set a code right now probably for the other sensor as well because I have it unplugged. Probably have a mass airflow sensor code right now too. Oops. Interesting. So open circuit voltage on, I think that's PCM side, and I'm on ground. I'm on AC. Go back to DC. There we go, 5 volts on the red wire, 5 volts on the black wire, okay? Make sure you guys can see that. So PCM side looks okay. Be careful, you don't really want to load test this. This is a signal circuit. There's not going to be a lot of amperage on this circuit, right? So I don't think we want to go putting a bulb or anything on there. And then let's grab the sensor itself, which I think is red and green on this harness. And the other one was black and white, I believe. So I'm just putting on a couple of the breakout leads here from the AES Wave kit. And we're going to just go ahead and run an ohm test across here. And Toyota actually does have a spec on this. Let me bring that up for you guys. Through their procedure, which you're supposed to follow because that makes for really good diagnostics, get into the PCM and all this other fun stuff. 120 to 280 K ohms, 1,000 ohms. So good old OL on that one, and we'll bump to the other pins to compare to the other side, and 200K. It might be hard for you guys to see. So 200K on there, OL on the other side. So I think we proved out at this point that we have an open circuit for Knox sensor bank 2. Obviously this testing would take just a few minutes to do that, but now comes the hard part of actually getting to it because it is under the lower intake manifold. So I kind of wish I could just say I'm done and that's the end of the video, but I think I'm going to go after actually replacing this and replacing this thing and showing you guys the replacement procedure. All right, any questions? Yeah, register for TST in advance. It gets more expensive the day of. So if you're thinking about going, make sure to register in advance. All right, so this is already prepped. The intake, the wiper cowl is off of here. So that wiper blades and everything would normally be right here. That's already off of here. There's also a bolt and a nut on this side and 2 bolts on this side on the back of the intake that I went ahead and have already removed just to help with the ease of ripping this thing apart. We do have to pull the lowers, so unfortunately I'm going to go ahead and drain the coolant out here. Get that draining. Just so we can go ahead and not make as big of a mess when we get this all apart. All right, and then I guess I'll just start in on this and start ripping this apart. Now, this would be a good point for a time lapse, but we'll see how long this takes. This is kind of a bigger intake manifold job. There goes the CO beeper. That's annoying. Let's see if that cup is over here. We'll just muffle that a little bit. And let's see what we got. So obviously if you're in the shop, you've probably pulled these intake manifolds off numerous times before to do spark plugs and that kind of thing. This part, I guess, is intended more for the DIYer, somebody who's looking to do this at home, that kind of thing. But yeah, but just remember, the t-shirt giveaway is at the end, so you got to bear with me here. We'll get this done quickly. Normally I don't do a lot of the actual repair during the video like this just because it does take quite a bit of time, but I did get a lot of this prepped ahead of time, so it should be hopefully a lot faster than what I think it's like 3 point some hours to do this job normally. Wow. Now the fans are kicking in. Oh, and there's a train today. You guys are getting all kinds of awesome feedback. All right. So I'm going to pull the radiator cap so our radiator drains out a little quicker. Set that off to the side. Never fails that you end up dropping the bolts down the intake manifold, so a good idea to pull those out, get those out of the way right away. And I think I'm just going to try to flip this thing off to the side. It does have two coolant hoses. Okay, I think we're back. Sorry guys, having a little bit of computer issues here. I think we're back. Sorry about that. Okay, we're back. Sorry. I think we lost the computer there for a second. All right. Let me know if it goes down again. So I was disconnecting coolant hoses here. I don't know how much you guys missed. Hopefully not too much. We're about to get the intake manifold off, pulling these two hoses that are on the throttle body. You might be able to pull these two studs out and get this thing flipped over. But since I'm already draining coolant anyway, I'm just going to go ahead and disconnect these. There's one. All right, now we should be able to be good to go. Maybe? Somebody's still attached on the back side. Yep, there we go. There's a looks like a crankcase breather hose back on the back side there, holding the back side of the intake down. Maybe that's it. Oh wait, there's more. Okay, well, I guess it was just kind of stuck on there, but there's our upper intake manifold. We'll get that off out of the way. I'm just going to throw a rag over here for now because we will be pulling the lower off. I'm not going to bother taping it up like I normally would because it's about to be off of this engine. Pull our injectors. Looks like we got a ground over there. All right, heater core hoses right here, running off to the heater core. I think I'm going to leave those attached for now. We're going to see if we can just flip the intake up and over. If you want, disconnect them to get the intake cleaned up better. We'll see what that's like after we get that far. I do have a fuel connection somewhere here that's going to have to come apart. Looks like right here. Plastic cover where the nylon line meets the steel line. I should have probably drained the fuel system before this, but we'll put a rag over it. Safety first. Throw some safety glasses on. And let's see what we got here. So this is a pinch, the two yellow pieces on the connector right here. I should probably be wearing gloves as well. I forgot them at home. But if you're in the shop or anytime you're touching fuel, put some gloves on. You don't want to be soaking that into your skin. All right, so it looks like we got a bunch of bolts here in the intake, on the lower intake that are going to have to come off, and I think that's probably about it yet, okay? Is that light making it better or worse? We'll leave it off for now until we get down in there. I believe these should be 12 millimeter bolts here. Yep. They also have a Torx in the middle. I probably would not suggest using that. More likely to strip out. They do have a 12 millimeter head on them. Somebody, Keith, you're going to send me a link to Bosley right now? Is that bald spot right there? It's starting. It sucks getting old. All right. I'm going to have to start wearing a hat like Eric O does. That way you guys can't see my bald spot starting. So there's a nut right here in this corner. I'd suggest being careful when you're taking it off. I believe there's one in the opposite kitty corner, but you don't want to go dropping it in there. And then also underneath that nut is a sneaky little washer, okay? Don't pull the lower intake up and drop this little guy down into the engine, okay? You will have a very, very bad day. And I believe there should be, yep, there's one back in. Oh, no, that's a bolt back there. I believe there's one other. If that happens again, just click on it and then hit go. But I have to still change it on this side. Christ. Don't bring up my laptop here. Come on. Come on. Technical difficulties if you guys can hear me. Okay. Okay, I think we should be back. I just canceled the wrong camera. Okay, I think we're back and I think we'll be okay. I dropped a couple of the cameras off to hopefully reduce the load here. So now we'll just have okay, good? Make sense? Okay, sorry about that guys. We're just having computer issues today. I think the CPU is having some issues inside of our switcher. So I dropped a couple of the cameras, so I won't have the side shot anymore, unfortunately. And I don't have the scan tool hooked up anymore either. But I think we might be able to make it through now. We'll see. Is that everybody? No, one more. Of course I dropped my socket. Sorry about the issues, guys. Computer technical difficulties are never any fun. That back nut is over on this side. Right back here. Again, this is that nut with the washer. Don't drop that down the intake, okay? Okay, there's the nut. And the washer, okay? Don't drop that. Bad day. That should be everybody. Maybe? Oh, I lied. One more. Okay. So like I said, we're just gonna, oh yeah, look at that. We're just gonna flip this guy up out of the way. And don't set it on the battery positive terminal because that would be bad news. We'll clean that up later, but wow. Oh, look at that. That is nasty under there. Let me zoom you guys in. Get some light in there. Look at that. That's kind of gross. Hopefully there's nothing living in there right now. Uh-oh, vacuum's plugged. Day in the life of the shop. Really? Well, guys, if it was easy, anybody could do it, I guess. So, I guess when you're sucking up mouse nests, make sure your vacuum has a bigger area so it doesn't get plugged up. All right, that's not working. All right, I'm gonna pull this, well, there's our harness. There's a clip. I'm gonna pull this hose. I think I'm gonna try to get this hose out of the way so we can get a good shot down in there and see what that looks like. I don't think this thing's going back together on cameras, guys. On camera, guys. This is gonna be way too long of a video. But I will show the find in a second here, I hope. I wish I had gloves on. All right, just gotta get the other side of the hose. Let's just cover these up quick. Otherwise, we're gonna have a bunch of stuff falling in there. And I will vacuum out each port before this goes back together. And of course, clean the gasket surfaces as well. All right. Wow. Sorry you're having to watch me struggle. There we go. That's just gross. Wonder what's all in there. All right. Well, there's our sensors. And get my head out of the way, sorry. I don't know. Try to get this unplugged. Oh, I can feel a broken wire. Oh, there's one. There's the other. Okay. Well, there's our problem. Success. Get some of this dilapidated harness out of the way, but green is not connected. So, very open circuit. As you can see, we found our issue. Now, we're, an hour into the job. It's really up to you at this point, and between you and the customer. Yes, I will wash my hands immediately after I'm off camera. I got a sink right there. It's up to you and the customer at this point. Do you just replace this harness, or do you replace the sensors already? I'd be willing to bet both of these sensors are probably okay. What we got here, 12 millimeter. Let me pull one of those. Let me pull the one that was reading bad out, and we'll just go ahead and measure. We'll do a resistance check on it. Now, you guys know I don't like resistance testing, but at this point, we're just simply measuring across a resistor element inside of there. And the socket's too long. So we could, there we go. All right, so the sensor's sitting on a stud, right, because it had a hole in the middle, so we got a stud. Here is the old one, just held on with a nut. Here's the old sensor, and we'll hook it up to the, I'll hook it up to the ohm meter here and take a look. But I would be willing to bet that this guy is probably still good. But I'm already in here. I've already unplugged it. I already have it in my hand. These aren't cheap sensors, but you guys should be able to see that. We're good to go. This sensor is currently passing an ohm test, okay? Now, if it gets heated up, if it is stressed in any way, does it stop working? Maybe. This is an 06. I'd be willing to bet that this is an original. This car is getting 2 new sensors, without a doubt. It's just doing the customer right. I mean, it's over 3 hours of a quoted job just to get this far. I think it'd be a disservice to the customer to not put sensors in. So I got 2 new sensors, our NTK sensors. Again, they always come in a bag. If it's not in a bag, it's been installed already, so just kind of nice to know it's in the bag. And then I also have a new jumper harness. Okay, so new harness, new sensors going in this thing, and that will take care of the repair. I wonder, did I leave the key on? If the key is still on, I'd rather not cycle the key. Okay, key is still on. I'd rather not cycle the key because I have the fuel system open right now. You're supposed to shut the key off before you do any of this work, because now I'm probably, I don't know, have 15 or 20 different codes stored in the system. But we're already past that point already, so 2 new knock sensors are plugged into the harness, and then I'm going to plug these into their respective harness onto the vehicle, and let's just throw them up on the scope real quick and just make sure that each of them are reading the proper voltage. And that'll be our confirmed repair, and then I am going to battle with this thing, putting it back together off of camera because, well, it's going to take a while, I think. Got a lot to clean up, got to fix my vacuum. So let's just go right into the back of the sensor harness here. And we'll go on the same traces we were on before. Oh, my probe is all bent out of shape. So we'll go on that one. And we'll go on this one. And I just need to make a note here after we're done testing that I need to not forget. Okay, so that's done. Let's see what we got. I don't think I have a good connection. So we're reading some interesting voltage, and probably because this thing is not happy with me right now. Just under a volt. Battery voltage is probably low on here because I've had the key on forever. But we're reading the same voltage for each sensor now. Okay, they're both doing the exact same thing. So I think we're good to go here. Now, when you're installing these sensors, I have to clean everything up in there yet, so I've got a little bit of work ahead of me yet. But when you're installing these sensors, torque and orientation of the sensor is critical for these things, okay? If you look in service information for the knock sensor, you will see that it needs to be orientated in a certain manner because that is the way it was designed. If you do it differently, it may not read, or it might be hypersensitive. Either way, it needs to be installed properly. If you under-torque it or over-torque it, you can also change the readings. Of course, torque sequence for your intake manifold, when you're torquing it back down, make sure you go in the sequence, or you can tweak or warp them. But here's our orientation of the knock sensor, okay? The connector of the sensor needs to be facing engine front, not vehicle front, engine front. We are facing the serpentine belt, okay? That is the direction that this thing is going. The sensor connectors are facing towards the belt, towards the serpentine belt train, not the front of the vehicle, engine front, okay? Front of the engine is where the serpentine belt is mounted on here. It needs to be orientated that way within 0 to 5 degrees of flat, and it needs to be torqued down to 14 foot-pounds, okay? Torque it down, make sure it's orientated right, plug it in, and we'll be good to go. I have a lot of cleaning to do, and I'm gonna, sorry, it's just, I'm touching my laptop, it's just gross. Okay, now we're a little bit more sanitary. So that just about does it. Everything's going to go back together the way it came apart. New gaskets, always put new gaskets on. We're putting new coolant in here. If the coolant was in good shape, you might reuse it maybe if you want. But we are putting new coolant in. It is the Toyota Asian specific coolant, the pink coolant that's going back in here. Everything will be torqued down, and at the end here, the car will be happy. Now, unfortunately, I'm not going to be able to get you guys the 3,000 RPM ignition advance like I had said, but I probably got at least another hour in getting this all cleaned up and back together, because that is just kind of disgusting under there. And then I'm going to suggest this customer invest in some mouse traps or something like that to hopefully stop this from happening in the future. Questions? Oh, I got the t-shirt question yet. Okay. Yes, service information, Terry. Service information is key on here. You need to make sure they're torqued, because the sensor element itself inside of there is a small, like almost a ceramic wafer. It's a piezo ceramic wafer inside of there basically, and that's what vibrates and generates our AC voltage. If you over torque that thing, you can crack it, and then it's not going to work. If you under torque it, the sensor can vibrate on its own without the engine harmonics. So no ugga-duggas on that one. Torque wrench for sure. Okay, yeah, measuring the new sensors. Sure, I can do that quick. That's a simple, quick, easy thing. So again, here's the old sensor still hooked up. If you want to go to the overhead, 202, and old sensor, and that's 202,000 by the way, 202K, and the new sensor. So 2 ohms less on the new sensor. And we'll do the other one. There we go. Okay, so the new sensors test out good according to an ohm reading, but you guys who have been a part of this training for a long time, you know I'm not the biggest fan of doing an ohm test. Ohm resistance testing does not stress anything. It doesn't stress the system. It doesn't stress the sensor. It's not operating under the conditions that it would operate at on the vehicle. So ohm testing is not high up there on my list. But we do have a spec. We have something we can compare against. So I guess in this instance, it is a good, valid, quick check, and it only takes a minute. Anything else? I could, I might try that, Keith. I might over torque the old sensor just to see what it does to the sensor. Okay, t-shirt question. Here we go. Technician A says, a knock sensor is used to advance the ignition timing event in the event of engine knock or pinging. Technician B says a knock sensor is not used to prevent pre-ignition. It is not used to prevent pre-ignition. Who's correct? A, B, both, or neither? I also want an answer of why, okay? Don't just give me Tech A or Tech B or both or neither. Give me a reason why. Now, we do have an updated email address here. Let's leave it up there full screen just so, yes, please, so they can see it. There you go, perfect. mcbecker@ngksparkplugs.com. Send me out an email. Again, I'm only giving away 5 t-shirts. So right here, email address, I'm only giving away 5 t-shirts per broadcast. So first 5 guys in from this moment on will win a shirt. Again, the giveaway is only valid for today. Okay, so if you're watching this video 2 years from now, unfortunately it's not valid. You're more than welcome to send me out an email with your answer, and we can have a conversation back and forth. We can talk about why that answer is that way, or whatever it might be. Whatever you want to talk about, shoot me out an email. If you have something interesting going on in the shop, you want to share a story, you just want somebody to talk to, email one of the other guys. No, just kidding. Send me out an email. I'd be happy to help work through whatever issue you're dealing with. You know, maybe you'll have an awesome story that we can share on the broadcast, like Mike Burton had that Porsche that time that he was working on, where we shared that story. So it's just awesome to be able to share all that information out there. So unless there's anything else that you guys want to see, my throat is starting to get raw. Good old time of being sick, right? Anything else? Mike, you ask a great question. I might be doing that lesson coming up next month. He asked if those wires are still underneath my truck. What was it? Probably over a year and a half ago now. I think it was 10 wire connections, like wire nuts, a twisted pair, a solder connection, a heat shrink butt connector, and I put those all underneath my truck to drive through a couple Wisconsin winters to see what would hold up the best. Now they're still on my truck today, and I'm thinking maybe they're going to come off in the next few weeks, and that might be the next broadcast next month. We'll see. That might be what we're going to cover next month. I guess you'll just have to join in and see what it is that we're doing. Send me out your email. My phone is buzzing in my pocket, so I think I'm getting emails from you guys. Unless there's anything else that you want to see tested on here, I'm gonna jump off the camera here and get this thing back together. I really appreciate everybody being there. Please give us a thumbs up. Subscribe if you haven't already. Click that little bell icon so you get notifications when we go live. Other than that, I'll see some of you guys at the TST event here coming up at the end of the month. Otherwise, we'll see everybody else on April 4th at 11 o'clock. Alrighty, so thank you everybody for watching. I really appreciate it. We'll see you again next time in the NGK Tech Garage. Happy wrenching, everyone. Thank you.